Hello everybody. The topic for today is universal quantum gate decomposition. So we will start with rotation gates and we will see that how the quantum gates can be decomposed using the uh, rotation gates as a universal feature. Now rotation gates are parameterized quantum gates. So if they are parameterized, that means the behavior depends on one or more continuous parameters, typically real valued angles. These parameters make since these angles are parameterized quantities, so these parameters or angles will be used to make such gates tunable, allowing them to be optimized during quantum algorithms, especially for variational quantum algorithms and quantum machine learning. Now these gates act on one or more qubits and their behavior of quantum qubits changes with the parameter theta. Theta is the angle with which the rotation is asked for. Now let us do certain basics of rotation gates. There are three main rotation gates in quantum computing. So first gate is Rx theta, Ry theta and Rz theta. So x, y, z basically denotes the axis of rotation. Rx theta will rotate the qubit. Here the axis of rotation will be x-axis. In the case of Ry theta, the rotation axis is y theta, and theta will determine how much the qubit will rotate along the axis of rotation for the particular rotation gate. The matrix representation of Rx theta is e to the power minus iota theta by 2, and this is the poly x gate. For Ry theta, that means rotation gate, so y rotation gate is similar to the rotation gate for x-axis, but only the replacement of the axis of rotation is here. So therefore the matrix representation is e to the power minus theta by 2 y, and in the case of Rz theta, here the rotation axis of rotation changes and it becomes z. So these are the three important rotation gates which are basically based on the poly matrices. Now Rx theta, the equation for Rx theta is given by cos theta by 2i minus iota sine theta by 2 x. So if you solve this equation, you will be able to get this matrix, and you will similarly get the matrix for Ry theta and Rz theta. So these are the matrices. If you substitute the value of theta in this matrix, so you will obtain the unitary matrix corresponding to this rotation gate. Now let us try to understand the fundamentals of single qubit rotation gates that we obtain from the poly matrices. This is to be understood in a more concise way and more depth. In more depth, we need to understand the fundamentals of single qubit rotation gates. So let's study this. Now, a single qubit rotation is a unitary operator. So it will be, for example, I have talked about Rx theta, Ry theta, Rz theta. So this will be a single qubit rotation. So it is a unitary operator. So unitary operator is U. Now it will belong to a special unitary group. This is important. We need to understand these facts because the degrees of freedom for the rotation gates will change with the unitary gate, with the special unitary group. We will see how. So this rotation gate is a unitary operator U that will belong to a special unitary group. That means matrices. So what is this group? This group contains all the 2 cross 2 unitary matrices with the determinant equal to 1. This is a condition. So all the rotation gates that we just discussed here, and the matrices thereafter. So all these matrices are unitary operators. So they belong to a special unitary group. All matrices are 2 cross 2 unitary matrices, and the determinant will be equal to 1. So here is a simple note to understand. So therefore, SU in the bracket there is capital N. So SUN stands for special unitary group of degree capital N. It is group of all n cross n unitary matrices. In our example that I just discussed, we considered SU2. But I am putting up in the note I am putting up a general case where I am taking the group with capital N as the parameter. So is group of all, this special unitary group will consist of all the unitary matrices n of size n cross n. So if they are unitary, so therefore the matrices will fulfill this condition, which is the adjoint of U multiplied by the matrix itself will give me the identity matrix, right? Now this is another condition which we need to understand, is that all these unitary matrices will have determinant equal to 1. So mathematically speaking, how we can put the SUN how we can put the definition of special unitary group. So it is put like this: special unitary group of all n cross n unitary matrices is given by, so this U is unitary, and the element, so this is complex numbers domain. So all the elements of the unitary matrix can be complex numbers. So n cross n is the dimensionality, where the matrix dimensionality will be n cross n, such that the matrices are unitary matrices. That means the adjoint of U multiplied by the matrix itself will give me the identity, and the determinant of the matrix will be equal to 1. So this is a condition, this is the definition of special unitary group of degree capital N. Now if we consider special unitary group of dimension 2, now this will be a group of all 2 cross 2 special unitary matrices. It describes all possible single qubit rotations. So whatever the single qubit rotation matrices that I have previously discussed, those matrices will fall in this category. Now up to a global phase, because in quantum computing we are more concerned about the relative phase rather than the global phase. So up to the phase which has not reached to the global phase, so that phase is important and that phase must be considered. But once the global phase comes into picture, so for the observable, this global phase becomes ineffective basically. Now for example, this U is given by, so please try to understand, there are two abbreviations we have to keep in mind. One is U, the other is SU. So U denotes the unitary group, SU denotes the special unitary group. So unitary matrix means it will fulfill the condition of U adjoint multiplied by U gives me identity. But it may or may not have a determinant equal to 1. But in the case of special unitary group, it will also have the determinant equal to 1. So that's the difference between U and SU, right? So in general, this unitary matrix will be considered of this form, where alpha e to the power iota alpha gives me the global phase term, and these elements will be there in the unitary matrix such that mod A square plus mod B square will be equal to 1. Now the global phase e to the power iota alpha is not observable, so the physical gate lies in SU2. So that means we can just ignore this global phase. So therefore, all polymatrices sigma x, sigma y, sigma z generate SU2. So all the polymatrices like poly x, poly y, poly z, these unitary matrices can be used to generate special unitary group of dimension 2. These types of matrices, how? Via exponentiation. This is a process by which we can obtain the rotation gates. Now this is the definition or the method of exponentiation in this equation, which says that R, this n is the unit vector which basically describes whether it is x, y or z. So R, in the subscript, it is unit vector n of theta is given by, this is how we can generate the rotation gate, e to the power minus iota theta by 2, where n cap dot sigma is the dot product between this unit vector and sigma is all the polymatrices. So this is my sigma, which gives me all the polymatrices, and this is n cap dot sigma, which is a vector. So this gives the dot product. Now the exponential form generates all elements of SU2. So this exponential form or this method of exponentiation can be used to generate all the elements of the SU2 group from which will be the rotation gates. Now let us see about SU2 and rotations. Every SU2 matrix can be written as a rotation. So therefore, this U theta comma n is the unitary matrix and it can be written as a rotation gate by method of exponentiation just now discussed also, where n cap is the unit vector axis. Now if this is the case, if we get U, right, with the conditions that we have just discussed, what are the conditions? That U will be a unitary matrix, U will be having a determinant equal to 1. So that means it will belong to a group of special unitary matrices of dimension 2 cross 2. Now there is a universal theorem which we need to understand. That's why the title of this topic, the title of today's lecture is Universal Gate Decomposition. Now what is this universal theorem? This theorem basically states that universal single qubit rotation, meaning by any single qubit unitary SU2, a single qubit unitary will have dimensions 2 cross 2, can be decomposed. Now this U can be decomposed as e to the power iota alpha, which is the global phase. We can ignore this, of course, and further in the decomposition will come a RZ rotation with angle beta, RY rotation with angle gamma, and again RZ rotation with angle delta. This is also known as, where alpha, beta, gamma, delta are real parameters, and this type of decomposition is also known as Euler's angle decomposition or ZYZ decomposition of quantum gates. Why ZYZ? Because we are first applying RZ gate, then RY gate, and then RZ gate again. So that is why this is also known as ZYZ decomposition of quantum gates. Now we need to understand one more thing when we deal with the basics of the special unitary group and the unitary matrices, is that we have to consider the factorization. We have to see, we have this U2 matrix. What is U2 matrix? U2 matrix is a unitary matrix. What is the condition for unitary matrix? That the adjoint of this matrix multiplied by the matrix itself will give me the identity. So that defines U2. Now we can factorize this U2 into two things. One is global phase and the other is SU2 matrix. Now in the decomposition, if you look at, this is the unitary matrix and it can be decomposed into two things. One is e to the power iota alpha, which gives me the global phase, and the second part is Rz, Ry and Rz again, which is the SU2 matrix. So when we write the matrix for Rz beta, we write the matrix for Ry gamma and Rz delta, and we calculate the combined matrix. That matrix will fulfill the properties of SU2 matrix. That means this matrix, which results from Rz beta, Ry gamma and Rz delta, will have determinant equal to 1. And of course, this matrix, the resulting matrix, is unitary. So therefore, a unitary matrix, the story starts from a unitary matrix. It can be decomposed into two things. One is the global phase, one is SU2 special unitary group. So that's why this title, this heading is Factorization of U2 into global phase and a SU2 matrix. Now for any, that's what is being explained in this further in this title. For any U belonging to a U2 group, that means a unitary matrix with 2 cross 2 matrices, its determinant lies on the unit circle. Now the determinant lies on the unit circle. Now the determinant of U is given by e to the power iota theta. So this is by theorem, this is by mathematics, that the determinant of unitary matrix will be given by this. If we set alpha equal to theta by 2, alpha is basically our global phase term. So if we set alpha equal to theta by 2, we just substitute theta value of theta here, which is 2 alpha, we will get e to the power iota alpha equal to under root of determinant of u, because the power of 2 actually becomes the under root of determinant u. And if we have a matrix V, we can use matrix V. How? We will use matrix V which has e to the power minus iota alpha and u. So what can we do with matrix V? We can eliminate the global phase present in the unitary matrix U. Now if you write, if you substitute, like I have done it here, if you substitute the value of u here, what you will substitute? You will substitute this e to the power iota alpha and rest of the decomposition. Now e to the power iota alpha and e to the power minus iota alpha term will cancel. That means the matrix V will help us in cancelling the global phase, and what will be left? The SU2 group, special unitary group 2. That is, you are multiplying every entry of u by the global phase e to the power minus iota alpha, which is a complex number of unit modulus. So this keeps it unitary. So therefore V matrix will remain unitary, and it will not have the effect of the global phase, and it kills the determinant phase, though determinant will be equal to 1. So therefore V matrix will be SU2 group but without global phase, right? So this property is there for any n cross n matrix. If we take the determinant of C, where A is some matrix, C is some scalar, it comes out to be equal to C to the power n determinant of A. Now in our case, we have n equal to 2, so therefore determinant of V will be equal to e to the power minus iota 2 alpha. So that is why I have written down here determinant in terms of the exponential value. Right. Now the pair alpha and V, so we can determine u from here, which is you take the e to the power minus iota alpha to this side, so our u will be equal to e to the power iota alpha V. V is a special unitary group. Basically, you must with this theory, what I am only trying to portray here is that there is a unitary matrix and there is a SU2 group. Unitary matrix will have global phase, SU2 will not have global phase. How can we cancel out the global phase from SU2? By just multiplying this u with e to the power minus iota alpha. That's only the meaning with this all mathematics, right? So ultimately we take V as the matrix which belongs to the SU2 group, and this can be written as, so if U as I have just explained, by using the method of exponentiation, I can from the unitary matrix I can obtain the rotation matrix. From the poly matrices I can obtain the rotation matrices. So this will be my rotation matrix using the poly vector sigma x, sigma y and sigma z, and this is the unit vector which will specifically determine whether we are obtaining V for x, or we are determining V for y, or we are determining V for z. So therefore we will obtain 3 rotation gates with the value of this unit vector n, either x, y, z. Accordingly we will choose the sigma value here, right? So if it is unit vector, if it is x, of course the magnitude of the unit vector will be 1, so there will be only x. So therefore it will be equal to e to the power minus iota theta, this is sigma. So actually by 2 is missing here, let me put by 2 here, so it becomes the complete equation. So this is now, this is the axis angle form which is, so there are 2 ways by which the SU2 matrix can be explained. One is the axis angle form. What is this form? This is the exponential form. The other is the Euler's form, Euler ZYZ form, which is basically this V is the SU2 matrix, right? And it is without global phase. It is given by RZ beta, RY gamma and RZ delta. So this is the decomposition basically. So what it means is that a single qubit rotation gate, I mean any, see, let me just explain the definition here. So that's every SU2 matrix which is a special unitary group 2, meaning by it is unitary and determinant is equal to 1. Now it can be decomposed as, if you ignore the global phase here, it can be decomposed as, so let me come back to at this point. Okay, so any SU2 matrix, it can be decomposed as RZ beta, this is a rotation gate with angle, this is a Z rotation gate with angle beta, RY gamma, this is a rotation gate with gamma as the angle, and RZ delta, this is the Z rotation gate with angle delta. So 3 angles we need to find out, beta, gamma and delta. If we find out 3 angles, we will be able to obtain the decomposition of any SU2 matrix. So let us say if we are given any special unitary group matrix, 2 cross 2 matrix, if we are given, we can decompose this matrix using the rotation gates. This is a very important concept in the design of quantum circuits, because we can, any unitary matrix, we can use the rotations to obtain the functionality of that matrix. So this is the universal gate decomposition kind of theorem that we can apply on unitary matrices to achieve the operation or operability, or I mean the functionality of the unitary matrix using the rotation gates only. Now we need to discuss the degrees of freedom. So since we are discussing 2 cross 2 matrices, so let us start from a general 2 cross 2 complex matrix. Complex matrix means all the elements of the matrix are complex entries. So the size of the matrix is 2 cross 2. So therefore there are 4 complex numbers which are the elements of this matrix. Now since there are 4 complex numbers, so it will have 8 real parameters. This 2 cross 2 matrix, we don't know whether it is unitary or SU2. We consider only any 2 cross 2 complex matrix. So any 2 cross 2 complex matrix will have 8 real parameters, therefore 8 degrees of freedom, right? Now if you enforce unitarity, if you enforce this U adjoint multiplied by U equal to I, so what will happen? The degrees of freedom will be reduced to 4. The 4 degrees of freedom will be cut. Now what happens if we enforce unitarity? What happens? What happens is, let us say this is a unitary matrix. The first thing with the unitary approach is that the sum of the magnitude squares of all the column entries will be equal to 1. This is the condition for normalization. So mod a square plus mod c square will be equal to 1, which is a real number. Mod b square plus mod d square is equal to 1, which is another real number, and the two columns are orthogonal, meaning by a conjugate multiplied by b plus c conjugate multiplied by d should be equal to 0. So this is a complex number, so 2 real entries. So therefore, if you enforce unitarity, the degrees of freedom will be equal to 4. 4 will be cut out. The total independent constraints will become 4. Now then we introduce we know that a standard 4 parameter form is like this. So this unitary is a standard 4 parameter form where you have the global phase, where you have angle beta, gamma and delta, right? If we remove the global phase, so therefore the degrees of freedom will be reduced to 3, from 4 to 3. So that is the advantage of, or that is the property, the characteristic of the SU2 special unitary group. For any unitary with determinant equal to 1, determinant is given by e to the power iota theta, and this is again the same type of theory that we have just discussed, with the dimensionality of the SU2 group equal to 3 real parameters. Now we can in general obtain the dimensionality formulas also. For example, if the matrix is only unitary and we do not consider the factor 2 here, that means we are not considering 2 cross 2 unitary matrices, we are considering n cross n unitary matrices. If it is unitary only, the degrees of freedom or the dimensions is given by n square. If it is special unitary group of order n, then the dimensions will be 1 minus 1 because of the removal of the global phase. Now the canonical form of the SU2 group, SU2 cross 2 matrix, is given by, this is the same kind of thing, this is the canonical form. Now any unitary, this U dash, we know that it is a matrix which belongs to SU2. Now this canonical form is a very standardized form which is 2 cross 2 matrix, which actually determines is a form which represents the SU2 group. Now we will use this canonical form to solve various numericals also. So let us see how we can use this form to solve the numerical problem. Now as I told you, any single qubit unitary can be decomposed as I have already discussed, Rz beta, Ry gamma, Rz delta. So how you will obtain this? So what you do is that you write the equation for Rz beta, Ry gamma and Rz. What are the equations? Equations I have just described here. These are the matrices Rx, Ry and R. Here it is theta, but for solving for beta, gamma and delta, you will put in place of theta, you will use beta, gamma and delta. So if you first you calculate Rz beta and Ry gamma, you multiply the two matrices, you will get this. And next you do Rz beta, Ry gamma and Rz delta, you will get this form equal to. As I said, this is the standard canonical form, right, for a SU2 type of special unitary group of matrices. Now you compare the elements. That means element A will be equal to this element, element A will be equal to this element, element B will be equal to this element. Now if you find out this is A, this is B, then you find out the magnitudes and what is the phase. Phase of A is argument of A. What is argument of A? Minus beta plus delta by 2. Minus beta plus delta by 2 is the argument of A. Argument of B is this, minus beta minus delta by 2, and of course this will be modulus 2 pi. So from here you can find out beta, delta and gamma. You have found out by from here you can find out gamma also, right? From this point you can find out gamma. Once you have from this gamma will be equal to, gamma will be given by twice tan inverse of this is a special function to find out the tan, arctan or the inverse of tan, which is twice mod B comma mod A. Actually we know that if you, what is tangent theta is y by x. So theta we can find out tan inverse y by x, right? Now this is, there are some problems actually when you try to find out tan inverse y by x as it is, because it will not determine theta for different quadrants. For example, in the first quadrant both y and x will be positive, and in the third quadrant both y and x will be negative. So in the third quadrant the value of angle will be quite large as compared to the first quadrant. So this function does not take care of the sign of y and x. So therefore in programming languages people use this formula, tan inverse twice of y comma x. So that's what is being used here to calculate gamma. So therefore we can find using this methodology we can find out the three angles beta, gamma and delta, and that is our job, to find out three angles so that any unitary matrix we can put it equal to the decomposition form. The decomposition is in terms of the rotation gates. First is the Rz rotation, then Ry rotation, then Rz rotation, and we have calculated the three angles. So this is the universal gate decomposition formulation, where any unitary matrix which belongs to the special unitary group 2 can be decomposed into rotation matrices with ZYZ configuration. Thank you very much. Thank you.